Hello guys, this is CodeNCode and this is the third lecture of this Graph Theory Part 2 series. In this lecture we are going to study about Lowest Common Ancestors or LCA. So first of all, before studying how we can calculate LCA of two nodes, it is important to know what is actually LCA. So let me take some examples. So LCA of two nodes is the first ancestor which is common to both. So LCA of 3 and 4, the ancestors of 3 are 3, 2 and 1, and yep, in the definition of LCA, each node is considered to be ancestor of itself. So the ancestors of 3 are 3, 2 and 1, ancestors of 4 are 4, 2 and 1. You see, the first ancestor which is common to both 3 and 4 is 2, so LCA of 3 and 4 is 2. Now LCA of 3 and 5, again 3, 2, 1, 3, 5, 4, 2, 1. So the first common node is 2. So the LCA of 3 and 5 is 2. Now the LCA of 7 and 8, that is this and this. For 7, the LCA is 7. Ancestors are 7, 3, 2, 1. And for 8, ancestors are 8, 7, 3, 2, 1. So the first common node, common ancestor to both 7 and 8 is 7. So that is their LCA. Or basically, if two nodes lie on the same path from root to some leaf, then the first one that appears before the second one, that is LCA. So if you find the LCA of 4 and 7, sorry, 2 and 7, then they lie on the same path and the first node that appears is 2, so LCA would be 2. If they lie on the different path like this, like 7 and 4, the node from which you go on to different path, that node is actually their LCA, and this helps in calculating distance between two nodes in log n time. So how we can calculate LCA or find LCA? Suppose we have to find LCA of these two nodes. So to find the LCA of these two nodes, the general approach is to take the node which is deeper, that is this node, let's call it node B, and raise this node at the level of A. Keep making jumps until you reach the level of the other node. So for that we must know the level of both nodes or every other node. So the level is actually the height from the root. So height of A from root is 1, 2, 3. So this is at height 3, this is at height 6, I guess. 3, 1, 2, 3, 4, 5, 6. Yes, it is at height 6. So the difference between their height is 3. So you would make jumps till the difference between them is 0. Between the difference between their levels is 0. So first thing we would calculate is the difference between their levels. So level of B is 6, level of A is 3, so the difference is 3. So you would have to calculate the level array. You can calculate it using a simple DFS run. This would be calculated in big O of n time for a tree. So now you know the distance between their levels is 3. Now it's time to rise B one by one till it reaches the level of A, or basically the difference between their level is 0. So while D is greater than 0, we would update B to be parent of B. So parent of B, as you can see, is this node. So in a single DFS you have to calculate two things. First, the level of each node and parent of each node. So parent of this node is this, parent of this node is this, parent of 1, this would be our root, parent of root is known, so you can store -1 there. Now B is equals to parent of B and D minus minus. So B would become this node and D minus minus, so D is 2. Now D is still greater than 0, so you would again update B is equals to parent of B, so B would become this node and D minus minus. You do this again. Now D is 0, so B and A are on the same level. First thing to do is to make both on the same level. Now since both of them are on the same level, we might have found an LCA. Why? See, assume if A was this and B was this, so you would raise B till B reaches A, or basically the difference between their level becomes 0, so B would eventually become equal to A, right? So if B becomes equals to A, which means this node actually is their LCA, because if A is this and B is this, we know the LCA is this node itself, right? So if B is equals to A, after performing this while loop, then we might have found an LCA, and that would be if B is equals to A. So after performing this while loop, if A is equals to B or B is equals to A, you can return A or B. That would be your LCA. Otherwise they are on the same level but in the different subtree. Now the time is to rise both of them one by one, together. So what we would do, either we can rise A and B till A is equals to B, or till parent of A is equals to parent of B. So while parent of A is not equal to parent of B, since you can see parent of A is this and parent of A is this and parent of B is this, they are not same. That is why we can update A to be parent of A, B to be parent of B. So basically they have made a jump of length 1. Now see, again we would check whether parent of A is equals to parent of B or not. Now parent of A is equals to parent of B, which means now their parent is actually their first ancestor, which is common to both, and hence now their parent is equals to their LCA. So now we would come out of this while loop and simply return either parent of A or parent of B. You could have also run the while loop while A is not equal to B. That would have done the same trick. While A is not equal to B, A is equals to parent of A, B is equals to parent of B, and then finally return either A or B. But I am going with this because the advanced currently we are learning how the actual LCA algorithm works, and then we would the novice approach, and then we would be seeing how the better algorithm works. For that, in the better algorithm we also use this condition, so I don't want to mess up with this condition. You can implement this novice approach with a while loop while A is not equal to B and A is equals to parent of A, B is equals to parent of B, but I'll go with this. So you are as familiar with the actual algorithm, or that is binary lifting, as possible. That is why I'm keeping the codes of both of the approaches almost the same. Now this is what your LCA functions look like. So first you would calculate their distance. Remember, we are taking level of B minus level of A. It may also be possible that A is deeper than B, so A can be here, B can be here, so the distance can be negative. So before calculating all of this, check if level of A is greater than level of B. If that happens, simply swap A and B, and after that the whole algorithm would work fine. First you would calculate their distance between their level, and then you would update B till their difference is equals to 0, their difference between their level. After that you check whether A is equals to B. If A is equals to B, that means A or B is actually the LCA. Otherwise we would update both A and B simultaneously, and we would do this till parent of A is not equal to parent of B, and finally we would return parent of A. And this is the whole LCA algorithm for and this is the novice approach. The problem with this approach is that the space and time complexity, the space complexity is okay because we require big of n space, but to calculate each LCA we may have to do roughly big of n operations, or complexity would be big of n for each single LCA call, which is too much. So consider this was your graph, or this was your tree, and you need to find LCA between this node and this node. That in this case you need to make this node jump of n minus 1, and that would result into big of n complexity. So the novice approach is implementation wise okay, but the time complexity is too much, so we can't afford to go with novice approach. We have to learn something better. But before we do that, if I go and explain that approach, that is binary lifting, in this video, this is going to be a huge a very large video, and I don't want to do that. So here is homework for you. First, implement this algorithm, that is noise approach of calculating LCA of two nodes by yourself. The reason I'm saying this for you to do, as I've already explained, the code of this noise approach and the binary lifting approach matches mostly, like 60% 70%. So I want you to implement the noise approach so you are familiar with most of the code. So when we would be studying binary lifting, you won't be feeling like, okay, this is everything new and it would take time. So most of the thing you would be knowing yourself. And the second thing is the time complexity, because we are making a jump of length 1 and again repeatedly. If distance is d, we have to make a jump of length, we are making d jumps of length 1. So what do you think, instead of making a jump of length 1, what length jump should we make? And keep in mind about the time complexity, space complexity. So these two things are your homework. Just try to answer the second one, keeping in mind about the time and the space complexity, how we can reduce time complexity of making a jump of length, say L, not of length 1, but how would that affect the time and space complexity? Think about that. So in the next video I'll be explaining binary lifting, and till then just keep coding and complete both of your homework. So thank you guys for watching, and keep coding. Thank you.